Right, good day everyone. I'm just doing a video lesson on acids and bases. So it covers the grade 11 and the grade 12. The only difference is that in grade 11, we are going to end somewhere. We don't do many calculations. But when we go to grade 12, we are going to do calculations. So let us listen in. So we said the topic is acids and bases. So acids and bases, we are basically looking at two things here. We are looking at acids and we are looking at bases. So the first thing that you need to know here, you need to know the characteristics of acids and you need to know the characteristics of bases. So let us summarize them, but I'm going to give you some notes, PowerPoint notes on this. So when we look at acids, we know that generally acids have a sour taste. Acids have a sour taste. So when we say they have a sour taste, that does not mean you should go into your lab at your school and then you try to test hydrochloric acid, because it is very dangerous. But let us think of acetic acid, vinegar. You know, when you drink vinegar, when you are eating chips, you know the taste of vinegar, it is an acid. Lemon juice, or the liquid from a lemon, it is also an acid. So that is basically giving you an idea of what we mean when we say it has a sour taste. Acids, they can conduct electricity in an aqueous solution. Acids, they react to an indicator. When you put an indicator, they are going to make the indicator change color. We are going to look at that a little bit later on. When you react acids with metals, they are going to evolve or release hydrogen gas. Also, when you react acids with carbonates, we are going to see carbon dioxide gas being produced. So those are some of the characteristics. And we also know that for acids, they have a pH which is very low. Remember the pH scale, it is from 0 to 14. So acids have a very low pH. And then the neutral pH range is around 7, and then above 7 we know that that is the alkaline pH. So those characteristics, you need to know them. They need to be at the back of your head. But like I said, I'm going to do another document that I give to you guys so that you can see those characteristics. We also look at okay, let's look, before we look at what I wanted to talk about now, let's look at basically examples of acids. So examples of acids, we have hydrochloric acid, which is regarded as a strong acid. We also have what is called sulfuric acid. It is also a strong acid. We also have what is called nitric acid, HNO3. It is also another strong acid. We also have phosphoric acid, sorry. It is also another acid there. But let's focus on these three. So these three, they are referred to as strong acids. So when we talk about strong in chemistry, there is a way we need to explain. When they say, why do we say hydrochloric acid is a strong acid? We should be able to explain why it is a strong acid. And then we also have weak acids. Weak acids basically are organic acids. For grade 12, so you've already looked at a topic called organic chemistry, but for grade 11s, you may not have gone that deep. But basically, when you talk about organic acids, we are talking about our methanoic acid, our ethanoic acid, our propanoic acid, and so on and so on. So those are weak acids. So let me just give one example here. CH3COOH. This is a weak acid. So we are going to explain later what a weak acid is and what a strong acid is. Right, very good. Then we also now need to look at bases. So bases, they have a soapy feeling. They have a soapy feeling basically because they are also used in the manufacture of soaps. So they have a soapy feeling. They can also conduct electricity in an aqueous solution. And when they are in an aqueous solution, they produce a high concentration. They produce a high concentration of hydroxyl ions. They produce a high concentration of hydroxyl ions, OH minus. But when you look at acids, they produce in a solution a high concentration of H plus ions. So we are going to find many H plus ions if it's an acid, and we are going to find many OH minus ions in solution, that is if it is a base. Are we together there? Right, very good. So now, when you look at these characteristics, we said you must know them, make sure you memorize them, read them, understand them thoroughly. So we have now talked about acids and we've talked about bases. Now, we go on further now to define what an acid is, because we must use chemical terminology or chemistry terminology to explain what an acid is. And we must use chemical technology to explain what a base is. Is that okay? So first of all, we give credit to the scientists that postulated, that suggested, that came up or that studied these things. And some of them, they got Nobel prizes in science. So let us talk about a guy who was called Svante Arrhenius. So he was called Svante Arrhenius. So he came up with a theory that he used to define acids, and he also used the same theory to define bases. So Svante Arrhenius' theory on acids and bases. Right, let us start there. So first of all, the first thing that we want to find out is, what is an Arrhenius acid? So we call it an Arrhenius acid because it was defined according to this guy's theory or theory. That's why we call it an Arrhenius acid. So an Arrhenius acid, Arrhenius defined an acid basically as a substance that produces a high concentration of H plus ions in a solution. A substance that produces a high concentration of H plus ions in a solution. Are we together there? Right. Now, you may find that when you look at this, you are going to find that sometimes when you go over your textbooks or you go over material on acids and bases, you are going to find that sometimes they talk about a hydronium ion. Sometimes we say an acid is a substance that produces high concentrations of hydronium ions in solution. We are talking about H3O plus. Why H3O plus? There is a process that is called autoionization of water, or we call it autoprotolysis of water. You need to know that in a solution, when we have water, a water molecule, and then in that same solution, we have an H plus ion. These two are going to react through what is called dative covalent bonding. When we look at the types of bonding, we talk about ionic, we talk about covalent, but there is dative covalent or coordinate covalent bonding, whereby the normal Cooper structure of water is something like this. Let me just indicate them like this, just straight like this. So that is how we normally draw water. So when it is a coordinate covalent bond, it means we are going to have another hydrogen coming to the molecule, but it comes with nothing. So they are going to create that hydronium ion H3O plus. We'll look at that a little bit later on when we look at the types of bonding. Right, so sometimes instead of saying it produces a high concentration of H plus ions, sometimes we say it produces a high concentration of H3O plus. Why? Because once the H plus ion has been produced, the H plus is going to combine with the other water molecules that are available to produce H3O plus. So ultimately, instead of having H plus in the solution, we are going to end up having H3O plus. I think that is clear there. So let us look at an example of what Arrhenius was saying, because we already know by now, we said hydrochloric acid is an acid. So what does it mean? It means when we have hydrochloric acid, HCl, which is a covalent bond between hydrogen and chlorine. Covalent bond, it means they are sharing electrons. Remember, chlorine in its outermost orbital or outermost shell, it has 7 electrons, which is 1 short of being stable. And then hydrogen in its one and only orbital, it has 1 electron, and it is also short 1 for it to be stable because it has only 1 orbital. So they are going to share. So when the resources are not enough and we need everyone to benefit, what do? We share our resources. So these guys are going to share their electrons and they form what is called a covalent bond. So now, when this hydrochloric acid goes into solution, it is going to split up. When it splits up, it is going to produce H+. Then we write aqueous here to show that it is a solution. And then it is going to also produce Cl-, which again is aqueous. So the question is, how did I know that here it is going to be H+ and here it is going to be Cl-? When we go to our periodic table of elements, we know that elements in group 1 of the periodic table, which starts of course with hydrogen gas, they form bonds by donating their 1 excess electron. Because all of them are in group 1. Why? Because they have 1 electron in their last energy level. So they are going to donate that electron. So when they donate that electron, it means they now have an excess of positive charges. Because remember, when an element is or an atom is neutral, it means the number of protons, which are positive charges, is equal to the number of electrons, which are negative charges. But the moment it donates an electron, it loses a negative charge. So when it loses a negative charge, it means now the protons are now more than the electrons. It becomes positively charged because it now has more positive charges. So that's why we assign it a plus. It loses 1 electron. It is actually 1 plus. The coefficient of this plus is 1, but we don't write the 1. So that's why that's how I knew that hydrogen is going to be H+, because it's a group 1 element. And then I know that elements in group 1, they lose 1 electron as they take part in chemical bonding. Is it okay? Then how did I know that chlorine is going to be a minus? Chlorine is a group 7 element. So when it is in group 7, what does that tell me? It tells me that it has 7 electrons in its outermost orbital or outermost shell. And we know that according to the rules, for an element to be stable, it must have 8 electrons in its outermost shell. So if chlorine is having 7, it means it is not stable. So what must it do? It must get 1 electron from somewhere. When it gets 1 electron from somewhere, it becomes negatively charged because it now has more charges. Are we together there? So what do we call this process? That is the next question we must ask ourselves. Here we say this molecule is formed because of the sharing of electrons between hydrogen and chlorine. So the type of bond between these two is called a covalent bond. So if it is a covalent bond, this molecule, it is called a covalent molecule because it has been formed as a result of a covalent bond. So if it is a covalent molecule, what does it do in solution? If it's covalent, it forms ions for the first time. So this process is called ionization. It is called ionization. Ionization is basically a process whereby a covalent compound, a covalent molecule, forms ions in solution for the first time. These charges are called ions. We have cations and we have anions. So that is the process of ionization. Are we together there? So when we look at this now, according to Arrhenius' theory, he said an acid does what? It produces H+ ions in solution. So this confirms his theory or his theory. We can also look at another example of nitric acid, HNO3. I'm just going to look at monoprotic acids for now. Monoprotic means they donate 1 proton. We're going to explain all that a little bit later on in the next video. So this is nitric acid, HNO3. Again in solution, it is going to ionize. How does it ionize? It is going to produce H+ in aqueous solution and NO3- in aqueous solution. How did I know? Okay, Now we know that the H is going to be an H plus. We already explained that. But how did I know that the NO3 will carry a charge of minus? So these ones are called polyatomic ions. Polyatomic ions. So these polyatomic ions, they are radicals. It is a group of elements that combine together to form an ion. Remember, when you look at hydrogen ion here, H plus, this is just a hydrogen, which is one element, and we say plus. Chlorine ion, Cl, and a minus. But when you look at this one now, it is a combination of nitrogen and oxygen. So you need to know, these ones you need to know. You need to know that a nitrate, it is NO3 with a charge of minus. You need to know that a carbonate is CO3 with a charge of 2 minus. You need to know that a hydroxide is OH with a charge of minus, and so on and so on. You need to know that an ammonium is NH4 with a charge of plus. So this one is called ammonium. So these polyatomic ions, you have to know them at the back of your head because they are not going to be given to you. So this again proves that nitric acid is an acid because it produces H plus ions in solution. So now we understand what Arrhenius meant when he said an acid produces H plus ions in solution. Very good. So that was an Arrhenius acid. I'm just going to delete this here. I have a small board, so we are trying to economize the space. We now look at an Arrhenius base because we said the topic is acids and bases. So we want to now look at an Arrhenius base. For an Arrhenius base, we are just going to change something here, just a little bit. So it is a substance that now produces a high concentration of OH minus ions in solution. They are called hydroxide ions. Right, very good. So what are the bases? So the strongest of them all, the strongest base is sodium hydroxide. Sodium hydroxide. Now sodium hydroxide is a strong base. So this is sodium hydroxide like this. Then in solution, it is going to split up. But now, one of the characteristics of metals is that metals, they form compounds through ionic bonding. They donate electrons. All metals donate electrons as they take part in chemical bonding. If I can just take you back a bit, we talked about hydrochloric acid. If you look at hydrochloric acid, hydrogen is a non-metal. It is a gas. Everyone knows that. Although it is in group 1. All the other elements in group 1 are metals. Hydrogen is an exception. It is in group 1, but it is not a metal. So this is a non-metal, hydrogen. Chlorine is another non-metal. So always when two non-metals form a chemical bond, they do so by sharing electrons through what is called a covalent bond. Is it okay? So these are two non-metals. Two non-metals share electrons. It's a covalent bond. It's a covalent compound or a covalent molecule. Right, very good. But now let's look at sodium hydroxide. Sorry. When you look at sodium hydroxide now, the sodium is a metal. It is also found in group 1 of the periodic table. So if it's a metal, this sodium, the fact that it is a metal means what? Means it is going to donate its electron to the hydroxide. Are we together there? So that means the bond is already ionic, because an ionic bond is a bond where one element donates its extra electrons to the other element or the other atoms. So this is an ionic bond. So if it's an ionic bond, it means this is an ionic compound. Remember, covalent bond, covalent compound. So this is an ionic compound. So in a solution, we don't say an ionic compound ionizes. An ionic compound now dissociates. It dissociates because it already has ions, so they are just splitting up. So we say it dissociates. So this process is called dissociation. Remember the first process for acids, we called it ionization, forming ions for the first time. But this one now is called dissociation. So when I was a student like you, it used to confuse me. How do I know that this is dissociation and how do I know that this is ionization? So I remembered it like this. If it is ionic, it must be dissociation. Ionic compound cannot ionize. So that's how I remember that. Okay, ionic cannot go with ionization. So ionic must go with the opposite, which is dissociation. I hope that helps you guys. Very good. So this sodium produces sodium hydroxide, sorry. It is normally called caustic soda or lye. Not lye for lying, it's this lye. So that is the common name for sodium hydroxide. So we are saying in a solution it is going to produce sodium plus and hydroxyl ions. The same applies. I can choose another base. I can choose another base just to explain my point. I can choose potassium hydroxide. It is also going to dissociate to produce K plus and OH minus in aqueous solution. Again, remember, like I explained before, hydroxyl ions, these are polyatomic ions. So you need to remember that a hydroxyl, it is OH with a minus. So that is what we are calling dissociation. So this guy, Arrhenius, Svante Arrhenius, a Swedish scientist, that is how he defined acids and bases. So his theory ends there. But then there were shortcomings with his theory. Shortcomings, we are talking about problems with this theory. It was incomplete, it was inconclusive. It could not be used to explain all the acids and all the bases. It's like, for example, if someone asks you, what is a snake? You say it is a reptile. If you say a snake is a reptile, fine. A snake, it is classified in the family of reptiles, but that is not a complete explanation, because a lizard is also a reptile, because a crocodile is also a reptile. So that is not a conclusive explanation. So the theory of Arrhenius was not conclusive because it could not be used, for example, to explain. Let's talk about, for example, these metal oxides. Calcium oxide is a base. We can also talk about magnesium oxide. It is also a base. We can talk about sodium oxide. These are bases. But as you can see, when you look at the bases, these three bases, let me just call them A, B, and C, you can see that they do not have hydrogen. So when you put them now in solution, it is not possible for them to directly produce hydroxyl ions, OH minus. So it means, according to Arrhenius, he was basically saying, if we follow his theory, we are basically saying these three are not bases. Are we together there? So then, those were shortcomings. There's nothing wrong with Arrhenius' theory, but it just has some shortcomings. So there are two scientists who advanced studies, who used Arrhenius' theory and then they tried to perfect it. So these two scientists, they are called Johannes Bronsted and Thomas Lowry. Johannes Bronsted and Thomas Lowry. So they came up with what is called the Bronsted-Lowry theory. So Bronsted-Lowry, we have Johannes Bronsted and Thomas Lowry. So these are two scientists combined together. They came up with a theory. They were doing independent studies, but then they ended up combining their theories so that they could come up with one theory. So according to this theory, what is an acid? So this is a perfect theory which explains all acids and it explains all bases. What is a Bronsted-Lowry acid? It is a proton donor. Very simple. So you see that this is very easy to remember. And then according to this theory, what is a Bronsted-Lowry base? It is a proton acceptor. It is a proton acceptor. Oh, now this is very confusing because now we are talking about proton. What is this proton that we are talking about? Let us go back. When we looked at the structure of the atom, we know that at the center of the atom, there is what is called a nucleus. A nucleus, remember, it is not a container. It is basically a combination of nucleons. What are nucleons? These are protons and neutrons. We know that protons are positively charged and neutrons have no charge. And then around, so let me just draw something here to indicate what I'm saying. So the nucleus, there are protons, neutrons, protons, neutrons. So this is what makes the neutron, the nucleus. So the P naught there, it is representing protons which are positively charged, and this is representing the neutrons which are negatively charged. Then around this nucleus, in various energy levels, we are going to have electrons which are always orbiting, they are always revolving around the nucleus, and these are negatively charged. Are we together there? So we need to remember that. Now, what exactly are we calling a proton? Let us go to hydrogen. If we go to the periodic table of elements, and then we check hydrogen, we find that hydrogen, it has two numbers here. There's a 1 and then there's a 1. There's what is called the mass number, which represents the mass of the element, and then there's the atomic number, which represents the number of protons and also the number of electrons. This number means hydrogen has only one proton. So let us try to draw hydrogen. So the nucleus of hydrogen has only one proton. And then around this nucleus, we only have one electron. So that is hydrogen for you there. Right. So now, if that is the case with hydrogen, this is a neutral atom of hydrogen. One proton, one electron, no neutrons. Because to get the number of neutrons, we must say the mass number minus the atomic number. So 1 minus 1 is 0. Now, if we say H plus, we already talked about this. If we say H plus, the plus indicates that the hydrogen has donated an electron. It has lost an electron. So when the hydrogen loses an electron, let us just do it together here. When this electron goes, what is it that remains? Very good. When it loses the electron, we remain with a proton. Is it okay there? So the proton remains. So the H plus is what we call the proton. So an acid is a proton donor and the base is a proton acceptor. So this is the universally accepted explanation of acids and bases. It is the corrected version of what Arrhenius started. Are we together there? Right. So now, we need to look at certain equations so that we can identify what we mean when we say an acid is a proton donor and the base is a proton acceptor. Let us say I have hydrochloric acid here. And then let me react this hydrochloric acid with water. And then the products are going to be Cl minus and H3O plus. Let us look at this equation very carefully. Aqueous. Right, very good. So let us look at this. When I analyze this, I see that okay, this hydrochloric acid HCl, it started as HCl, but something happened to it, and then we ended up with Cl minus on the product. So when you analyze this carefully, you see that there's an H which is missing. It's actually an H plus. So the HCl lost an H plus, and then it remained a Cl minus. So I could say these two are connected. So when I look at it, I see that these two are connected. Because the HCl, it lost an H plus, and then it remained a Cl minus. Are we together there? Then the H2O. Remember the H plus that has been lost must go somewhere. So the H plus that was lost here, it was accepted by the water. That is why the water is now having the charge of H3O plus. It is now a hydronium ion. So it means these two are also connected. So these things that I'm indicating to show that they are connected, these are called conjugate pairs. Let me just write it down for you there. So we have what are called conjugate pairs. Conjugate, it simply means formed from. So the H plus that was lost here resulted in the formation of the Cl minus. So the Cl minus was formed from the HCl. So that is a conjugate pair. The H2O received a proton to produce H3O plus. So again, this is a conjugate pair because the H3O plus was formed from the H2O. So now we need to identify our acid here, and we need to identify our base. So our acid is a what? a proton donor. So when you look at these two, which one is donating the proton? It is clearly HCl. It is donating the proton to what? So this is our acid. Are we together there? Now the acid forms what is called a conjugate. It forms what is called a conjugate base. And this is pair number 1. So we call this one acid 1, and we call this conjugate base 1. This conjugate base was formed from acid number 1. Sometimes they can ask you to define a conjugate pair. A conjugate pair basically differs by an H+. It's either there is a shortage of an H+ or an H+ has been added. So that is a conjugate pair. This is the acid because it's donating the proton. This water is receiving the proton. So when it receives the proton, it is called a base, because we said a base is a proton acceptor. So this is a base number 2. Then a base forms a what? A conjugate acid number 2. So those are the pairs. Conjugate acid 2. Are we together there? So those are the 2 pairs that we are talking about. So sometimes you can be asked to identify the pair, so you just need to follow through there. You check, okay, these 2 are related, these 2 are related. Which one is donating the proton and which one is accepting the proton? Are we together there? So let me just give you a simple exercise that you guys can look at. So when you look at this exercise, then from there we shall continue. So I just want you to identify the conjugate acid-base pairs. So let's say we have these equations here. NH3 plus HCl, then we produce NH4 plus and Cl minus. Number 2, let us have water being reacted with HNO3, and then we are going to produce H3O plus NO3 minus. Then let me also have the same water. I want to this same equation. H2O, there's something that we are going to explain later. You are going to see something very interesting here. This water plus HNO3. This time, let us say it forms, that is a repetition now. It's not gonna work the way I want. Okay, let's have a simpler one. Water. Alright, it's fine. Let us have something like this. Maybe before we explain ampholites, let's have HCl. Plus, let's have what? Let's have water here, and then let us produce Cl minus and H3O plus. Then the 4th one, let us have water and water. Then water and water, let it produce OH minus and H3O plus. Right, let's do this simple exercise, just these 4 questions. You write them nicely, you identify the conjugate acids and base pairs, then we'll take it from there. Right, good one. Okay guys, welcome back. So I gave you an activity and then I hope you did the activity and then you saw that it was not challenging at all. So now we want to talk about what is called an ampholyte. So I've written the definition for you here. An ampholyte is a substance that can act either as an acid or as a base, depending on the conditions. Right. So here, let's look at these 2 equations that we've written here on the whiteboard. So let's look at the first one. Let's try together to identify the pairs. So when I check here, I see that this water is related to the OH minus. So these two are a conjugate pair. I can see that. Then I also see that NH3 is related to the NH4 plus. So those two are also a conjugate pair. So now let's identify the acid and let's identify the base. So the water is donating a proton to NH3. That is why it is remaining as OH minus. So my water here is going to be referred to as my acid number 1. That is pair 1. And then it produces a conjugate base. It produces a conjugate base. Okay, just call it a CV, also number 1. So we see the pair there. Then the NH3 is the one that is receiving the proton, so it becomes our base number 2. And then this one is now the conjugate acid. Conjugate acid 1. So we've identified our pairs there. When we come to the second equation, equation B, we see that now the water is receiving a proton, but it is still connected to the H3O plus. But in this case, the water receives a proton in order for it to become H3O plus. So the HCl in this case is the one that is now donating the proton. After donating the proton, it now becomes Cl minus. So this HCl is now our acid 1. Then the Cl minus is our conjugate base 1. Then the water is our base 2. And the H3O plus is the conjugate acid 2. So that is the situation we are having there. So now when I look at this, when I try to analyze this, I see that, what is happening here? Because in reaction A, our water is behaving as an acid. And in reaction 2, the water is behaving now as a base. So that means water is amphiprotic. Here's the spelling of amphiprotic. It means water can behave in one situation as an acid, and in another situation it is behaving as a base. So we say it is an ampholyte. We say it is amphoteric or it is amphiprotic. Are we together there? So there are several examples of ampholytes. We have HSO4 minus, we have HCO3 minus, H2PO4 minus, and so on. So you are going to be given equations. You need to be able to identify the ampholytes there. It does not mean it is always water. So there are several ampholytes. Are we together there? Now we want to define, we talked about strong acids, we also talked about weak acids. So we want to try and explain, to say what is a strong acid and what is a weak acid. So let us make that distinction there. Alright, so let me write the two equations. So if we can have these two equations here, we have HCl, hydrochloric acid. We said it is covalent. It's a covalent molecule. So if it's a covalent molecule, it is going to ionize. Remember that. So the process here is called ionization. We talked about this. So it is going to ionize into H plus ions, aqueous, and Cl minus, aqueous. And we referred to HCl before as a strong acid. That is how we referred to it. And then I'm going to have another example. CH3 COOH. Again, this one is going to split into CH3 COO minus and H plus in aqueous. This time, this one is referred to as a weak acid. So we need to understand the difference. Why are we saying hydrochloric acid is a strong acid, and why are we saying vinegar or acetic acid or ethanoic acid is a weak acid? So it is explained like this. When an acid is strong, we say a strong acid completely ionizes in solution. That is how we define a strong acid. And we say a weak acid, partially ionizes in solution. A weak acid partially ionizes in solution. So what are we saying? What are we talking about? We said ionization is the process whereby a substance forms ions in solution for the first time. So let's look at this. So when we talk about complete ionization, let me give you this example. We are saying, for argument's sake, let us say we have, on the reactant side, I have 5 HCl's. Okay, let me just put 4. I have 4 HCl's. What does it mean when we talk about complete ionization? When I talk about complete ionization, I'm saying all these HCl's are going to form ions. So in my solution, I'm going to have 4 H plus ions, and I'm going to have 4 Cl minus ions. Which means what? Which means all of them ionized. All of them separated into ions. So that is what we call complete ionization. So if a substance undergoes complete ionization in solution, it is referred to as a strong acid. That is the one and only definition of a strong acid. There were 4, all 4 of them split up, all 4 separated. If there are 5 million, it means all 5 million are going to separate. That is what we call complete ionization. And that is what defines a strong acid. Are we together there? Then, let's now use the same concept to try and explain a weak acid. A weak acid means what now this time? It means if I have 4 molecules of ethanoic acid, like in the first case we had 4 molecules, this time I'm also still having 4 molecules. So I'm having 4 molecules now. Then what happens now if it's a weak acid? If it's a weak acid, it means this first one will still remain as CH3 COOH. Nothing has happened. The second one still remains as CH3 COOH. The third one still remains as CH3 COOH. Only this one is the one that separates into CH3 COO and H plus. It means the other ones, majority of them are remaining intact, are remaining as they were. Only a few are the ones that are ionizing. We call that partial ionization. So when a substance partially ionizes in solution, it is called a weak acid. Let us repeat that. We said a strong acid completely ionizes in solution, and then our examples of strong acids, HCl, HNO3, and H2SO4. Are we together there? So now we understand the difference between a weak acid and a strong acid. Then let's talk about monoprotic and diprotic. Because when you look at acids, we need to understand that we have mono, we have di, we have polyprotic. If I look at, for example, HCl, when it ionizes, it's a strong acid. We already understand that now. It is going to produce H plus, and it is also going to produce Cl minus in solution. Are we together then? So when it takes part in a reaction, it is able to donate its proton, because according to the Bronsted-Lowry theory, an acid is a proton donor. So HCl can donate its proton. So when it donates its proton, it is an acid. And it can only donate 1 proton. So if a substance can donate 1 proton, we say it is monoprotic. Monoprotic means it can only donate 1 proton. It can only donate 1 proton per molecule. So we have this monoprotic acid. We also have nitric acid as a monoprotic acid. So these 2 acids are monoprotic. Are we together there? But let's look at an acid now like sulfuric acid. Sulfuric acid is H2SO4, and this one we refer to as a diprotic acid. So this one is a diprotic acid. Diprotic because why? It can donate 2 protons. Diprotic because it can donate 2 protons. What do we mean when we say it can donate 2 protons? Okay, we clearly see that there is an H2 here. So let us see. It means in the first reaction, we are going to have something like this. It is going to give us HSO4 minus and H plus. So that is the first proton that it can donate. Are we together there? Let's call this part reaction A. Then part reaction B, we now have this hydrogen sulfate ion. It can still donate another proton. We are going to have now a sulfate ion here and H plus. Which means what? Which means from sulfuric acid, we started with sulfuric acid, but this sulfuric acid is able or is capable of donating 2 protons. It can donate a proton here, it remains as hydrogen sulfate, HSO4 with a charge of minus, plus the proton. It can, the HSO4 minus, sorry, there is a minus here. The HSO4 minus can still donate another proton to produce H plus and SO4 2 minus. So this kind of acid, we say it is a diprotic acid. It can donate 2 protons. Then you would imagine that if we have phosphoric acid, it's triprotic, or normally we just say polyprotic. Poly means many. So a polyprotic acid is an acid that is able to donate many protons. So we understand what that means there. Then let's talk about bases. Since we defined a strong acid and a weak acid, we should also be able to define a strong base and a weak base. So let us go over that there. So for an acid, we said it ionizes because it is originally covalent. But for a base, like sodium hydroxide, remember it is going to form NH plus and OH minus. We also talked about these ones as bases. We talked about these ones as bases. So let's define now a strong base. So a strong base, we say it is a substance that completely dissociates in solution. That is a strong base, substance that completely dissociates. And then a weak base, if a strong base completely dissociates, it follows that a weak base partially dissociates in solution. So I'm sure we understand that again. So when we are looking at this, we are saying the strong bases basically are hydroxides. Hydroxides are the strong bases. Most of the others are weak bases. Is it okay there? So we now understand strong acid, weak acid, strong base, weak base. So the explanation is the same. It means if it is strong, it means they are going to split up all of them. If it is not strong, then they are not only going to split up partially. Then we now need to explain 2 other very important terms. We now need to talk about what is called a concentrated base. Concentrated base. But first of all, before we explain concentrated base and dilute, let us define concentration. There is a formula that we use for concentration. Concentration is basically equal to the number of moles divided by the volume, which gives us the units of mole per decicubic meter, because the SI unit for number of moles is the mole and the SI unit for volume is the decicubic meter. So that is why we are saying dm to the power of minus 3. It means we are dividing by dm to the power of 3, and then when we multiply, it goes on top, it becomes to the power of minus 3. So this is the concentration. It is the number of moles per unit volume. So it is the number of moles per unit volume. Like if you go to the shops, go to the shopping center. Yesterday I was also trying to stock up for the lockdown, and then I found that wherever I tried to go, there were many people. It was highly concentrated. It's the same supermarket, it's the same food chain where we buy our food, but this time there are a lot of people inside, so we say it's concentrated. The volume of the shop hasn't changed. What has changed is the number of people. So when you have more malls in that small volume, we say it is highly concentrated. Are we together there? And then the number of moles, from our stoichiometry, we know that the number of moles is the mass that is given in that particular instance divided by the molar mass of the solution. And then when we substitute that into there, we see that the concentration is equal to the molar mass, the given mass divided by the molar mass, all this divided by the volume, which is going to end up giving us this equation. So we need to remember also this equation when we are calculating concentration. But we are going to look at this thoroughly when we look at stoichiometry. So M is the given mass, which must be measured in grams. M is the molar mass, which is in grams per mole. And then V is the volume, which is in cubic decimeters. And then C represents our concentration, which of course is in moles per decicubic meter. So that is our situation here. So which means we can use this formula to calculate our concentration, or if we have the number of moles and volume, we can use that other one there. So when we say something is concentrated, it means we have a lot of moles. We have a high number of moles over a small volume. So let it not confuse us, because there is a common confusion. If I put one drop, for example, we already agreed that hydrochloric acid is a strong acid. And we agreed that acetic acid, this is a weak acid. So we already talked about this. So now, what happens if I put a drop of hydrochloric acid in a 5-liter container? If I put a drop of hydrochloric acid, just one drop in a 5-liter container, does that make the hydrochloric acid weak? No, it is still strong. But if I put a drop of hydrochloric acid into a 5-liter container, I now say my hydrochloric acid is dilute. Diluted means now it has been mixed with water. Are we together there? It is dilute, it has been mixed with water, but it is still strong. If it has not been mixed with water, we say it is concentrated and it is still strong. Even if I can put 2 liters of acetic acid and mix it with that 5 liters of water, maybe I choose a bigger container because the 5-liter container will no longer fit. But that does not make this acid strong. It is still weak, but it will be concentrated. So dilute means it has been mixed with water. Concentrated, it means it has not been mixed with anything. But still, when we define strong and weak, we look at ionization and dissociation. I hope we understand that. It is very, very important for us to understand that concept there. So I think for now we have looked at everything that we need to cover up to the grade 11 level. Then when we now go to the grade 12 level in the next video, we are now going to look at the base dissociation constant, the acid dissociation constant, and we'll also look at the ionic product of water and do some pH calculations. Thanks for watching, guys.